Hey, I'm going to do some constant velocity practice here. And this is a functioning pen, I think. There we go. All right. So let's see. Dog runs west. I guess if I'm thinking about a map like usual, that this is west and this is east. So like number line wise, probably west is like the negative direction and this is the positive direction. Dog runs west at a speed of 3 meters per second for 8 seconds. That's going to be 24 meters. Stops and sniffs the ground for 5 seconds and then turns and runs east 42 meters in 7 seconds. So that would be 6 meters per second there. What's the total distance traveled by the dog? Total distance doesn't care about direction. It's just like your odometer tracks all of the total distance that you have covered. So it looks like I got 24 meters, then nothing, and then 42 meters. So that is 66 meters of total distance. There's not much work to show there. If you wanted to really belabor the point, you could show the 3 legs of the journey that you're adding together. What's the net displacement of the dog from beginning to end? Okay, displacement is final position minus initial position. So if we imagine the dog on this like number line, the displacement is not going to change depending on where we start or where we set the origin. So I'm just going to say the dog starts here at the origin. Dog goes 24 this way, and then 42 this way. So 24 minus 42 is going to be sorry, a little slow. Is it negative 18? I think so. Hey, you're allowed to use a calculator in physics, so you can check my work there, make sure that that's right. All right. What's the dog's average speed for the entire trip? Well, the average speed is the total distance divided by the total time. So let's see, speed average is equal to the total distance. I don't want to write delta x here because that means displacement. Total distance over the total time. So my total distance is 66 meters. Total time is, let's see, 8 and 5 and 7 is 20 seconds. So, geez, I don't trust myself to do anything in my head now. 66 divided by 20 is 3.3 meters per second. How about the average velocity? Average velocity is delta x over delta t. That's displacement over time. So that's negative 18 meters over the same 20 seconds. So that's negative 0.9. Hey, I did that without a calculator. How about that? All right. Good. So velocity, average or otherwise, can be negative, speed, and distance cannot. So sketch a motion map. If you're in AP Physics, we're not going to do a lot with these motion maps. It's a thing I do a little bit more with in non-AP Physics. But I want to show you what one is, so you could skip this part if you want. It's a way of showing what's going on a number line. It's just a different mode of representation. So let's see, 24. Let's scale by 6s, shall we? So if I go 6, 12, 18, 24, and then this would be negative 6, negative 12, negative 18, negative 24. All right, so our motion map is just going to show us, so here, doggy starts at the origin. I get to pick where the origin is. I didn't have to pick it that way, but that works. So that's like a little dot at time 0. And then doggy's going to go every second. Doggy's going to go 3 meters for 8 seconds. So there's 1, 2, 3, 4, 5, 6, 7, 8. And there he is at time 8. It's time 1, time 2, time 3. So we're just putting little dots to show where the dog is at each time. Each dot represents 1 second going by. And when we have constant velocity, we put little arrows on these motion maps about halfway to the next dot to show that direction of motion. And if you always do them halfway to the next dot, then the size of the arrow kind of gives you a sense of how fast. Now, I didn't leave myself a lot of room here. Let's see, how am I going to do this? So then for 5 seconds, 1, 2, 3, 4, 5, the doggy stays still. So this is time 8, that's 9, 10, 11, 12, 13. And then for the next 7 seconds, doggy's going 6 meters per second in the other direction. Oh, dang it. I guess I made this backwards, didn't I? I should have made, sorry, these should have been going this way, and that should be going this way. But that is a good teachable moment here, my mistake, because we are the people who choose the directions of things. So although it would be maybe more conventional to choose west negative, east positive, that is an arbitrary choice. So hey, you could do it this way. So you just have to say, just indicate that this is west and this is east. So that's a little bit backwards to the way most people think about things. But look, oh, I fixed it. There. How about that? So either way, all depends on where you're looking from. One person's positive is the other person's negative. So that's what a motion map looks like. I'm not going to ask you to do those, but I just thought I'd just answer that part of the question anyway. So how about a position time graph? So let's see. Oh, I don't want to make that 0, I think. I think I better make my axis somewhere in the middle here. And this time, for this one, I will make east is positive. So I think I will scale it similarly. Let's see how many notches of time I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like I don't have another 10, so I think I better go by 2s. So I'll make that 20 right there. And then I'll scale this by maybe 3s. Does that give me enough? 3, 6, 9, 12, 15, 18, 21, 24. I go by 3s. And 1, 2, 3, 4. So that's negative 12 here. And negative 24. So I think that's going to work just fine. So we start here, and in 8 seconds, 2, 3, 4 of these notches, because I'm going by 2s, the doggy is going to go 24 meters in the negative direction, because I'm taking negative to be west here. What's the slope of that line? Pause. Well, the slope of that line is, it should be negative 3, right? That's the constant velocity from here to here. So the slope of that should be negative 3. Okay. For 5 seconds, 2, 4, and then half here, the doggy stays in place. So constant position. And then doggy goes, I know where the dog is going to end up, so I feel like the easiest way to make this graph is just to pick that point at 18 where I know the dog is going to end up and connect that. So that looks good. What's the slope of this? 6 meters per second. positive. All right. Okay. These are good questions. Cars traveling on a highway at 80 kilometers per hour, and a truck is traveling at 96 kilometers per hour in the same direction. Okay. They're both going in the same direction. Car starts out 40 kilometers ahead, and both continue to travel at their given speeds. Then how long will it take the truck to catch the car? Okay, well, let's see. If they're both going in the same direction, then I can put my origin down here because I'm not going to need any negative positions. And the car gets a 40-kilometer head start. So what do we want to count by? It's a little tricky to scale the graph because I don't know where they intersect. I don't know where my intersection point is going to be, and I'd like to include it in the graph. So I think that I'm actually going to do the algebraic version first. You could mess around with the graph and try to get a sense of it that way first. That would be fine. So what does it mean to do this algebraically? Well, show your work including the position function for each vehicle. So that's what I'm going to do. So my position of the truck, I'm going to call that x sub t, is equal to, I'm thinking to myself here, position is equal to constant velocity times time plus initial position. That's my little position function. It's a straight line, like a y equals mx plus b situation. So what's the velocity of the truck? The truck is going 96 kilometers per hour times time. And the truck's initial position is 0. So you could put plus 0 there if you want. I'm just going to leave it. And then the position of the car is going in the same direction, so also positive. Oops, that's kilometers, hours per hour. That's an interesting unit. Times time. But the car does not start at the origin. It starts 40 kilometers ahead. Right? Now, if you want to know when the truck catches up to the car, that's when they have the same position. So just like you've done a million times in algebra classes, we just need to set these two equal to each other to figure out when and where that happens. So I'm going to drop my units for the purposes of doing algebra and keeping it a little bit cleaner and less confusing. And then once I get to my answer here, put that there. But that's not the complete answer. That's just the time. So it takes 2.5 hours. That gives me an idea how I might scale this. But where do they intersect? Well, that's just a matter of putting this back into either one of these. So I think I'll put it in here. I can probably do that easier in my head. So 2.5 80s is 200. Right? 80 and 80 is 160, and then a half an 80 is another 40, and then another 40 that I'm adding on here. So the position where they meet is at 240 kilometers. All right. So let's make a graph now. It should be really easy to make the graph now that we know this. So I need to scale. This needs to go up to 240 and maybe beyond that. So let's see, if I scale by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's not enough. So let's scale it by 20s. So I'll go 20, 40, 60, 80, that'll be 100, 40, 60, 80, 200, 20, 40, 60, 80, 300. All right. And then my time, I need to get up to 2.5 plus hours. So 1, 2, 3, 4, 5. How about if I do, well, I guess I could do 6. And then if I had, if I cared about such things, maybe that's more natural for 1 hour, because then that would be like 10, 20, 30, 40, 50, 60 minutes, in case anybody cared about that sort of thing. 2, 3, 4, 5, 6. It's good. 1, 2, 3, 4, 5, 6. There isn't like a right and a wrong way to scale this, although my way is pretty nice here, gotta say. So long as you can see what you need to see in the graph. Okay, so the truck starts here, and then at 2.5 hours, I'm not going to mess with the slope. I think that's harder to graph that way. I'm just going to go out to where I know they're both going to be. So at 2.5 hours, that's here, it's at 240 kilometers. And, oh, look at that. Got a ruler right here. Sorry, at least that inches offends you. Get back to the metric side here. So, there we go. I'm presuming that the truck keeps going after it passes the car. The car starts at 40, which is right there, and it goes through that same point. That's the when and where of the passing. All right, so there we go. Cool. And similar here, two runners are 200 meters apart, both initially standing still. Runner A starts running toward runner B at a constant speed of 6. Okay, so they're running toward each other. So right away, that should indicate to me they're starting 200 meters apart and they're running toward each other. So they're going to have opposite slopes, opposite directions, which means one will be positive slope, one will be negative slope. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Perfect. So we'll make that 200 meters. Make this 100 meters. Okay, and 3 seconds after runner. Okay, let's see what we need to decide. We need to make a couple decisions here about who's going which way, and that is for us to decide. There's not a right and wrong about that. Two runners are 200 meters apart, both initially standing still. Runner A starts running toward runner B at a constant. I think I'm going to make runner A start here. 3 seconds after runner A begins running, runner B starts running toward A. So I'm going to take a chance here. I'm going to make this just scaled by 1 second. So runner B starts 3 seconds later. Right? Okay, so let's see if we can take this approach here and write these position equations. So position for runner A. Let's see. Runner A's velocity, speed is 6. Velocity, if they're going to be the one going this way, then we need to make sure that we get this negative sign here. And runner A does not start at 0. Runner A's initial position is 200, according to the way we have set things up here. So there's the position function for A. Runner B. Okay, how are we going to do this? Because I don't know where this intercept is. You could probably figure that out, but I'm going to use point slope form here. So, or you could also think of this as just sort of like shifting the graph. So I'm going to do it like that. This is a line that's going to have a slope of 5, and it goes through the point 3, 0. Right? So in point slope form, that would be like position minus 0 equals this times t minus 3. You could also just think about the way that you have learned in, I don't know, Algebra 2 pre-calculus about shifting functions. If you put a minus 3 here, that shifts something. Instead of a line that goes through the origin, it shifts it 3 units to the right. So that's another way to think about it. You could also just kind of dial this back and say, oh, well, I know where the intercept, if they're going 5 meters per second this way, then that would be like -5, -5, -5, or an intercept of -15. That works too. Okay, so now that I've got that, I can set these equal to each other and see where they intersect, and that's going to make things easy, super easy to graph. Okay, so I've got negative 6t plus 200. I'm going to get rid of the units just for the purpose of doing the algebra a little bit more easily. I'm going to distribute my 5t minus 15. So looks like I got 11t equals 215. So the time is about 19.5 seconds. And the position is, I can plug that into either one of these. So about 82.5 meters. All right, so this is the when and the where of them passing each other. Let's see if I can find that point on here. 19.5 seconds, so this is 5 seconds, 10, 20, wait, 5, 10, sorry, 15. If you're counting by fives, 15 comes after 10, and that'd be 20 seconds. So 19.5 seconds and 82.5. These are scaled by tens. So 80, that's an 80, and that's 20, so 82.5. A little bit up from there and back. So something like, right about there. There it is. Got a little too enthusiastic about my lines there. Sorry about that. All right. Great.